So rational exponents basically means any exponents that are fractions. A rational number is a number that can be written as a fraction. So we're going to talk about when you have fractions as your exponents. And they can also be written as a radical. So we have two forms here. This is exponential form, and this is radical form. So if it's written as a rational exponent or a fractional exponent, that's called exponential form. And if it's written as a radical, that's called radical form. And so b raised to the 1 over n, that denominator becomes your root in the radical, or the index in your radical. Basically all of this. So to write this in radical form, that becomes the 6th root of x, because that denominator becomes the index, and that's it. And then to go the opposite way, when you're given a radical form and you're trying to write it in exponential form, this becomes the denominator, so it's z raised to the 1/4. So for these, this is the 7th root of a, and this one is, and you don't have an index here, but that means that it's a square root. So that means w is being raised to the 1/2. So the next rule is when the numerator is not just a 1. When it's just a 1, it's pretty easy, just like the ones we did, it just becomes the radical. When it's not a 1 and you have a numerator on that fraction, that becomes the exponent. So it looks like this. And it's the nth root still, because the n is my denominator, and that still goes in my root or my index. The numerator becomes my exponent, and it can be the exponent inside the radical on that b or whatever that base is, or it can be that root all being raised to that exponent, whatever that numerator is. So for example, if I have 27 raised to the 2/3, this is going to become the cube root, because my denominator is my root of 27. It's going to be easier if I do it this way in this case, because I can take the cube root of 27, which is 3, and then 3 squared becomes 9. Rather than, I would still be allowed to do it this way, but squaring 27 is going to be a little bit larger, and then I'm going to have to take the cube root of it. It's still going to equal 9 if I do it that way as well. These first two are still with 1 as the numerator. So this in radical form is still going to be the 5th root of a. And this one is still going to be c raised to the 1/8, because there's no exponent here. So the numerator is still 1. But when we get down here, so to write this in radical form, the way I remember it is, this is the root, I call sometimes. So where do roots from a tree go? Underground, underneath. The root comes from under the fraction bar, the denominator part. So that's my root, the 4th root of d raised to the 7th. And of course you can write this as the 4th root of d and that whole radical raised to the 7th. Either one of those would be okay. And then this one is going to be, okay, so I'm going the opposite way into exponential form. 3 is my root, so that's going to be my denominator, and -5 is my exponent, so that's going to be my numerator. So you can do operations with these as well. I have y raised to the 1/7 times y raised to the 4/7. So because the bases are the same, I can combine them. And if you remember what to do with the exponents, you add the exponents. Now in this case, the denominators happen to be the same. If not, you got to remember your fraction rules. In order to add fractions, you have to have a common denominator. So in this case, it's quite easy because the denominators are the same. But if if they ever are not, you have to find the common denominator first. So this becomes y raised to the 5 over 7, which you could also write in radical form, which would be the 7th root of y to the 5th. You can leave it in exponential form, but you could also change it to radical form. There was an earlier example where I ended up with a negative exponent as a fraction, and I can't actually leave it that way. So here is I'm going to show you how you can rationalize it, because what that means is basically that negative, remember that negative exponent brings it down to the denominator. And when you have that fractional exponent in the denominator, it means it's a radical in the denominator. And I can't have a radical in the denominator, so I have to rationalize it. So what I'm going to do here is multiply it and to make this a whole number instead of a fraction. So what can I multiply it by to make it a whole number is going to be 1/3. And whatever I multiply in the numerator, I also need to multiply in the denominator, or the other way around. Whatever I multiply in the denominator, I also need to multiply the numerator. So this becomes x raised to the 1/3 over x raised to the 1st. And this is the rationalized form of x raised to the negative 2 over 3. So I'll give you a second, pause it, go ahead and try both of these as the you try problems, and I'll give you the answers in 5 seconds. So this first one is you add the exponents, p raised to the 10 over 4, which reduces to 5 over 2. You could also have it as the square root of p to the 5th. The next one, the negative exponent moves that term down to the denominator, and if you didn't understand what I meant by that's really a radical in the denominator, well, that's the 5th root of r to the 4th. And remember, we need to rationalize that, so you're multiplying it by something to make it a perfect 5th root, which is just r to the 1st. You can do it this way as well. You may see it a little better doing this way with the fractions, and I get r raised to the 1/5 over r. These next three have to do with those exponent rules as well. These bases are the same, they're both x, so what I do with the exponents when I'm dividing is subtract. So I have x raised to the 3/4 minus 1/2. And to add or subtract fractions, I need that common denominator like I was saying before. And these don't have a common denominator, so I need to make it first 3 over 4 minus 2 over 4. And I multiply both these by 2 to get the common denominator of 4. And that becomes x raised to the 1/4. So that would be your simplified form, or you could write it in the radical form, which would be the 4th root of x. In this one, if the roots were the same, I would be able to subtract the exponents, and I would be able to put it under one radical and then subtract my exponents, and that would be fine. Because the roots are different, I can't use that rule. But if you notice, they are both x. So what I can do is change them to exponential form. So I can change them. This one's going to be x raised to the 3 over 4 divided by x raised to the 2 over 8. And if you notice, now I can subtract them just like I did in the previous one. And if you notice, 2 over 8 reduces to 1 over 4. So I get x raised to the 2 over 4, which reduces to 1/2. So it's x raised to the 1/2, or you could write that in radical form, square root of x. And this last one, your exponent rules. This exponent goes to each part of that monomial. So I have 16 raised to the 3/4 times 8 raised to the, y raised to the negative 8 times 3/4. And I'm going to simplify each of those separately. This becomes the 4th root of 16 raised to the 3rd. Well, in this case, it's going to be easier to take the 4th root of 16 and then raise it to the 3rd, which will become 2 raised to the 3rd, which is 8. And then I'm going to do the y part, and I have y raised to the, when I multiply these together, that becomes negative 24/4, which is equal to y raised to the negative 6th. So I get 8 times y raised to the negative 6th. And now I have a negative exponent. Remember, you got to move that to the denominator. And it doesn't have a radical anymore. It's not a fraction, so I don't need to rationalize it. That's my answer. So go ahead and take a little bit and try to do these 3 on your own. And you can pause it, and I'll give you the answers and explain it in a little bit. But first, understand I can't multiply these radicals together, the 3 and the 3 like we used to, because they're not the same radical. But if you notice that the radicand is the same, change it to exponential form, and then your base will be the same. And then you can use your exponent properties. Same thing with number 2. And then with number 3, you're going to have to change this to exponential form rather than that radical, and then you can use the exponent rule with that power to a power. So for this first one, again, I can change them to exponential form. 3 raised to the 1/2 times 3 raised to the 1/4. Now I can add those exponents. The 1/2 needs to change to a denominator of 4, so that's 2/4, and add them, and that becomes 3 raised to the 3/4. Or you can write that as the 4th root of 3 cubed, or the 4th root of 3 cubed is 27. Any of those would be okay. So for number 2, I change it to exponential form. The numerator becomes x raised to the 3/2. Remember, this is a square root, so my denominator becomes 2. The denominator becomes x raised to the 2/3. So you're subtracting them. 3/2 minus 2/3. Got to find a common denominator, so that becomes 9/6 minus 4/6, which is x raised to the 5/6. And you can write that in radical form. That would be the 6th root of x to the 5th. So to simplify this last one, remember I'm using my power to a power rule, so I distribute this to each part of that monomial, the 9, the x, and the y. Notice I changed the y to exponential form. It's y raised to the 1/4. So 9 raised to the 3/2, that becomes the square root of 9 to the 3rd. The square root of 9 is 3. 3 to the 3rd becomes 27. And then x raised to the 3/2, that doesn't simplify, so that's the part in my answer. And y raised to the 1/4 times 3/2, power to a power, I'm multiplying the exponents, and that becomes multiplied straight across, 3/8, and that doesn't simplify, so 27, x raised to the 3/2, y raised to the 3/8. All right, back on the jokes. This is a decent one. This is a good one. What do you get when you cross a cow with a volcano? An utter disaster. The cow's udder. Woo!